So today we'll be beginning our discussion of stoichiometry, which is the study of relative quantities or amounts of substances taking part in a reaction. So the study of stoichiometry allows you to predict how much product you're going to make from a given amount of reactant, or if you need a certain amount of product, you can figure out how much reactant you need to start with in order to get that. So stoichiometry is something that you use all the time as a chemist, pretty much any time you're doing a reaction. You know, if I know I want 1 gram of my product to be able to study it, or maybe I want 10 kilograms of my product if I'm working in an industrial setting, I can use stoichiometry to figure out how much starting material I need. So there are lots of different places where stoichiometry will come into play, where this is going to be something that you will continually revisit throughout your chemistry education. So what stoichiometry does is uses the coefficients in a balanced chemical equation in sort of a new way. So you've seen chemical reactions before, you've balanced chemical reactions, and you have likely been thinking of them as the number of molecules that are reacting and the number of molecules that are produced in a chemical reaction. But now that we've introduced the concept of the mole, the way that chemists count things, if your coefficients represent the number of molecules, since a mole is just a constant number of things, it can also represent the number of moles of molecules that are reacting or produced. So that's usually how we're going to be thinking about it, since in the lab we're usually working on a molar scale, that we're usually working with, you know, a mole or more of stuff, or a sizable fraction of a mole at least. So we're usually going to think of coefficients from here on out as representing how many moles of stuff are reacting. So all we're really doing in stoichiometry is using those coefficients and using the ratio of those coefficients to determine the relative amounts of stuff. So we're essentially taking our coefficients from our balanced reaction and we're using them as a conversion factor from moles of one substance to moles of a different substance. So we're going to do a few different examples to kind of see that in action. So the first one, we're going to use this reaction of water reacting to form hydrogen and oxygen. So our balanced chemical equation is shown here, that 2 moles of water react to produce 2 moles of hydrogen and 1 mole of oxygen. Remember that anytime we don't have a coefficient written in front of something, it is implied to be 1. So these two examples are going to show us sort of how we can utilize stoichiometry at its most simple, in its most simple way. So the first question asks us, how many moles of oxygen are produced if 6 moles of water react? So there are 2 different ways you can kind of think about stoichiometry, and I'm going to go through both for these first couple examples. You can think of your chemical equation here as a recipe, that just like if you were making cookies, your ingredients are butter, sugar, flour, eggs, etc., and you get a product. You put in those reactants. Some chemical reactions do actually happen when you're baking, and you get the product that is cookies. Our ingredients here are 2 moles of water, and our product that we're trying to make is 2 moles of hydrogen and 1 mole of oxygen. So just like you would scale up or scale down a recipe, that maybe you're having a party and you need a lot of cookies, so you're gonna double your recipe, you can do the same thing here. So if we take a look at this, and our recipe uses 2 moles of water, but we want to use 6 moles of water. So essentially, instead of using 2 moles of water, we're using 6, which means that we have tripled our recipe. So in order for this to stay balanced, we need to apply the same thing, the same factoring, to all of our reactants and products. Just like if you use 3 times as much flour baking cookies, you better use 3 times as much eggs and 3 times as much sugar as well. And you would expect to get 3 times as many cookies. So if we multiply these also by a factor of 3, if we're starting with 6 moles of water, since we've tripled our recipe, we would expect to produce 6 moles of hydrogen and, I wrote this incorrectly, sorry, and 3 moles, 3 times 1 is 3, and 3 moles of oxygen. So that's kind of the logical way that you can think through it. You can also think about it more mathematically, which is how we're going to do most of our problems, is by taking our coefficients from our balanced reaction here, taking our coefficients and using them as a conversion factor. So what our coefficients are telling us, we're looking for how many moles of oxygen are produced if 6 moles of water react. We know from our formula, from our reaction, that 2 moles of water react to produce 1 mole of oxygen. So just like any other conversion factor, we can use this in the same way that we were converting between grams and moles last week, between moles and number of particles, the way you would between feet and inches. You can do exactly the same thing here, where you're thinking of it as converting from moles of one substance to moles of a different substance, in this case from moles of water to moles of oxygen. So if 6 moles of water react, we're going to use our conversion factor, and dimensional analysis tells us that if I want to convert out of moles of water, that needs to go on the bottom so that it cancels, and I want to end up in moles of O2, so that goes on the top, and then we're just plugging in our coefficients. So these are coming from our balanced reaction. 2 moles of water, 1 mole of oxygen, and 6 times 1/2 gets us 3 moles of O2. So we come up with exactly the same answer. When your numbers are really, really simple, it's nice to be able to think through it this way, to think of it kind of by the recipe method. When your numbers are a little bit more complicated is when this method generally becomes easier or more straightforward anyways. And this is the way that chemists typically express their work. We like to show our unit conversions by dimensional analysis, so it's important to be able to use this method as well. Even though this one oftentimes, the recipe method oftentimes kind of makes more sense intuitively, being able to express how you got there mathematically is also an important skill. So we can think similarly on this next problem, how many moles of water must react in order to produce 12 moles of oxygen? So now our question is asking us, how do we produce 12 moles of O2? So our coefficient for oxygen in our standard recipe, our typical balanced reaction, is 1. So to get 12 moles of oxygen, we're going to need 12 times as much stuff. So if 12 moles of oxygen are produced, we would expect 24 moles of hydrogen to be produced. And in order to do that, we would have needed to consume 24 moles of H2O. So everything is being multiplied by the same factor. We're just scaling up our recipe, this time by a factor of 12. So by our sort of recipe method here, we get 24 moles of water, but let's do it out by the conversion factor method as well. So we're doing something very similar here, just kind of going in the other direction. That we want to know, we want to produce 12 moles of oxygen, and we're trying to figure out how much water we need to be able to do that. So in this case, we're using the same conversion factor here. That we did before, that 2 moles of water produces 1 mole of oxygen. But now we want moles of oxygen to cancel, so that's going to go on the bottom. And moles of water is the unit we're looking to end up in, so that's going to go on the top. The coefficient for water is 2, so the 2 goes wherever you put moles of water. The coefficient for oxygen is 1, so that goes along with moles of oxygen in our denominator. So again, these are coming from our coefficients. And now we have 12 times 2 is 24 moles of water. Since our units of moles of O2 canceled moles of O2, up there we were canceling moles of water to end up in moles of O2. So which way your ratio goes depends on what unit you're trying to end up with. So let's take a look at a slightly more complicated reaction and some slightly more complicated examples. So if you would like to pause the video here and take a moment to do these on your own, feel free to do so. So in this reaction, we've got a bit more going on. We have 5 moles of silver reacting with 1 permanganate ion and 8 hydrogen ions to form 5 silver ions, a manganese 2 ion, and 4 water molecules. So we have a little bit more going on, a little bit less straightforward coefficients. And we're asked first how many moles of water are produced when 8.6 moles of silver react. So this one is a little bit less straightforward in terms of like how much are we scaling this up by. Our recipe uses 5 moles of silver and we're actually reacting 8.6. It's not a nice, integer multiplication. So this is where the conversion factor method is often more straightforward, I think. So we're asked how many moles of water are produced when some number of moles of silver react. So those are the two things that we want to relate here. So if we pull in our coefficients for those two things, we have 5 moles of silver react to produce 4 moles of water. So that's our conversion factor. That 5 moles of silver produces 4 moles of water. And now we're told that we're starting with 8.6 moles of silver. So to cancel that unit, moles of silver needs to go on the bottom of our conversion factor. We're looking to convert into moles of water, so that's going to go on the top. And then we just plug in our coefficients. So the coefficient for silver was 5, so that's going to go on the bottom with moles of silver. And coefficient for water was 4, so that's going to go on the top. So now when we do out that multiplication, we'll end up with 6.9 moles of H2O. And then our last example with the same reaction, how many moles of hydrogen ions must react in order to completely consume 4 moles of silver? So now we're still looking at silver, but instead of relating it to how much water we're going to produce, we're looking to now relate it to how many hydrogen ions must react. We want to make sure we have enough of all of our reactants. So to figure out how many hydrogen ions there are, we're going to look at that relationship. Our 5 moles of silver in our reaction reacts with 8 moles of hydrogen ions. So our conversion factor is that 5 moles of Ag is equal to 8 moles of H plus in this chemical equation. So now we can do the same thing. We have 4.2 moles of silver that we're starting with. We want moles of silver to cancel, so that goes on the bottom. And the new unit we want to end up in is moles of H plus. So that goes on the top. And then we plug in the appropriate coefficients. The coefficient for silver was 5. Coefficient for H plus was 8. So these are coming from our balanced reaction. And then when we do out that math, we get 6.7 moles of H plus must be there in order to react all 4.2 moles of silver.